Today's session is about brain swelling. We will be examining a brain specimen that was obtained from a 38-year-old woman who was found dead with extensive bruising to the body and head. A post-mortem examination revealed a large right-sided subdural hemorrhage. At the macroscopic level, we see significant flattening of the surface of the right cerebral hemisphere, which is here. We also see a marked swelling of the deeper cerebral structures in this region, here. Anteriorly, this degree of swelling displaced the falx cerebri, causing subfalcine herniation. Posteriorly, the swelling of the uncus resulted in a subtentorial herniation here. The latter was accompanied by pressure necrosis, where the swollen uncus was compressed against the skull.
We'd now like to show you some of the microscopic features of brain edema, as opposed to the macro specimen where we were looking at an individual who had suffered a subdural hemorrhage. Here we are going to look at someone who has actually suffered an ischemic stroke within 2 to 4 hours of their death. In other words, we're going to be looking at a new infarct. Now, infarcts or new infarcts display what we call ischemic topography, and what we mean by that is that we have if we go from the infarct itself on the left-hand side, we'll go through an area of edema, and then we'll go through an area of brain that has got some blood supply but not necessarily adequate, and then we'll move away into normal brain. Now, if we look at these areas in more detail, for example, here is an area that's quite close to the infarct itself. And this area we call the penumbra. And what we see of the neurons within the penumbra, because neurons are most susceptible to hypoxia, some of the neurons have started to take on a rather unusual and a rather reddened look, and in fact we call these red neurons. And these neurons may or may not survive depending on how soon their blood supply can be returned, either naturally or perhaps through thrombolytic therapy if this person had actually been treated or successfully treated. Of course, this is the area that we've been most interested in, and this is the area of edema that is actually surrounding the infarct itself. Edema, of course, associated with inflammation. In the live person, this area would have been full of fluid or interstitial fluid, but in this section we're now left with just open space. So this is what edema looks like on a microscopic specimen. The other thing I'd like to draw your attention to on this specimen is that if we then move closer and into the infarct itself, is that now all the neurons have taken on this characteristic reddened look, and in fact most of them have lost their nucleus and will die irrespective of whether the blood supply was returned or not. And compare it with these particular neurons down here. They also look reddened, and what's happening here is that the nucleic acid part of the neuron or within the nucleus is being lost, and so these neurons are losing their characteristic hematoxylin or blue staining, whereas the cytoplasmic component is not lost as quickly, and so they appear to be red or red neurons, but all of these neurons will succumb to the process. So this is what happens in a recent injury in the brain, something like an infarct. We get this build-up of edema. It's both cytotoxic and vasogenic in nature, and though this might not be the case in most ischemic infarcts, in injuries such as what we saw with a subdural hemorrhage, this edema can become so significant, combined with the original mass, it can exceed the size of the intracranial space, and once that's exceeded, we get problems like herniation, and then we also get the intracranial pressure becoming greater than the cerebral perfusion pressure, and very rapidly we get firstly neuronal death, then eventually brain death and death of the individual.